I first thank the organizers and particularly Susan and Andy for inviting me here. It's quite exciting. It's almost like my debut because I knew nothing about the kinase and probably still know them, but I have been working on it for almost 3 years, so it's very exciting to report to the experts here. And well, it's very hard to do any talk following Benoit. It's hard to not look at speaker. But Benoit's computer died first. So let me put the acknowledgement first, because really without everything that I'm reporting here is made possible by the molecular dynamics infrastructures and the tools that have been developed in Yibing Shan research or DESRES, and so that's quite a privilege to take the first hand using these tools. And almost all simulations I'm going to report here are run by Desmond, which is very good, very fast parallel MD code, and it's freely accessible to academia people. So check it out. And also, I can learn the whole talk with technology. Also, thanks David for, when 3 years ago I said I wanted to do kinase, and David basically asked me, what do I know about kinase? I said, probably nothing. And they said, sounds good enough for me. So that's how it started. And well, what I'm going to report here is also largely the results come from collaboration with John Curran's lab. The collaboration started a few months after we started the kinase project. So without John's input, I'm sure that the project would take a very different shape and probably much less interesting. And Marcus Siliger, who's sitting there, is the main person working on the experimental side of the work I'm going to report here. And I interact with Marcus on a daily basis, maybe not quite daily, but on a regular basis, and it's certainly very helpful and productive, and it's fun. So that really comes stuff. The main part of the talk, I'm going to talk about our work on DFG flip, or enable kinase. So of course, the DFG motif is very well known. When 6 years ago I was in San Diego working in structural genomics, a startup company, and I actually heard about DFG motif before I heard about the kinase. So it's a very well-known 3 residues located at the center of kinase catalytic center, and the DFG motif, aspartate, phenylalanine, and glycine, the motif is almost universally conserved in eukaryotic kinases, and that implies that it has very important functional roles. And recent studies, particularly this Nature paper in the year 2008, 2007, find out that mutations on the DFG motif very often drives the oncological process. So basically, if nature wants to create a cancer, one of the favorable places is when to mess up is the DFG motif. And in terms of pharmaceutical considerations, DFG motif is very important for designing kinase inhibitors because it's so important that kinase inhibitors are traditionally classified into type 1 and type 2 according to the particular DFG conformations they recognize. So it really plays a central role. So here comes a cheap plot, but here it comes. Recently, it's reported in New York Times that Sergey Brin, one of the three Google founders, carries a DFG mutant. And this mutant predisposed him to develop Parkinson's disease in the future. So that's just, well, we use him as a poster boy for the therapeutic clinical importance of the DFG motif. So okay, so I will stop here. Now, how it looks like the DFG motif. Here's the kinase, and the upside is a smaller N lobe, and we have a larger C lobe. Between these two lobes, it lies the ATP binding site, and the DFG motif is located right in the center of the binding site. With, this is the aspartate. At the other side, the aspartate here was showing that it's in the kinematic binding site. So we call it a DFG in conformation, and the phenylalanine is not in the binding site. And then this is the other conformation, we call it DFG out, because the aspartate has left the binding site, and the phenylalanine has entered the binding site. So between the DFG in and the DFG out, look at this. If my two palms are represents the two side chains, that's the conformational chain. So that's the conformational chain. One leaves the binding site, one left, one enters the binding site. Now, so we started to tinker with the Abel kinase. The Abel kinase was the first kinase I started tinkering with and running long simulations, and it was a very quite a steep learning curve. But after a while, we see that the DFG motif seemed to be reasonably flexible, so that got my attention. So maybe we can do something just focused on the DFG motif. So we started banging simulations on it. What happened was that we noticed two things. One is that we estimate for whatever reason, we started estimating what's the pKa of the aspartate when it's in the binding site, ATP binding site. And we find out it has a very elevated pKa. It's about 6.5. This kind of estimation are not very accurate, but it's sure that it's very elevated. So if it's 6.5, it doesn't take too much free energy to protonate this aspartate. Then the other thing we noticed was that in one of John's earlier structure of autoinhibit Abel, which adopts a DFG out conformation, we noticed that the aspartate in that DFG out conformation must be protonated, because otherwise it just wouldn't choose that conformation for the aspartate. It clearly forms a hydrogen bond between aspartate and something else, and there's an invisible hydrogen. So at that time, the keyword protonation enters our thinking. We say, okay, let's protonate this and then run it. And we start running it, and we do see much enhanced flexibility of the DFG motif. It seemed to be telling me that it wanted to flip. It wanted to flip after protonation, but we didn't really see that in the wild type. So we started tinkering, see what's the simulation trying to tell us. And at the end, we introduced the mutation. This is supposed to be Abel M298. So it's a methanine at the helix alpha C. Is one of the spine residues, and we noticed that this methanine, the hydrophobic residue, is in the way of the flipping. It's negotiating. It's engaging in a very slow negotiation with phenylalanine. And when the negotiation succeeded, we anticipate that the flip will occur. So based on that intuition, we removed that massaging and ran that again, and we were very lucky to be able to simulate the simulation. So, well, I guess I didn't start from you. So, let me set it up again a little bit. So now it ended the DFG out conformation. Okay, with the phenylalanine entered the binding site and the aspartate, which is the red residue, left the binding site. So I think I didn't show the initial conformation very clearly. Let me do this again. So this is the initial conformation on this able M298 mutant with the aspartate in the binding site and the phenylalanine out of the binding site, and the aspartate has been permeated. So now we try to do this again. It started. Now this is sort of, it's a vertical, and it's the phenylalanine is trying to enter the ATP binding site and negotiating with a lot of hydrophobic residues, and the aspartate is now it comes in. Okay, so that's the simulation. So obviously that makes a reasonable movie. We were excited about that. Then we try to learn as much as we can. So what does this simulation basically, this is a number of snapshots we took from the simulation. And these are real conformations from the simulation. And this column represents the alpha C helix, which has been mentioned many times in this conference. And these are the conformations of the DFG motif. Of course, basically, what this is telling us is that the helix has to move out, leaving the ATP binding site to make space, allow the DFG flip to occur. This is just a different representation of what I was trying to say. And basically, again, the helix has to move out and creating space for DFG flip. And we see that the DFG flip involves quite significant conformational change at the DFG loop. And this is just a cartoon saying the same thing. And initially, you have the alpha C helix in the binding site. You have the DFG in conformation, and then you have the helix moves out, which Carol has been talking about, Benoit has been talking about. And then you create space at this area that allows the DFG flip to occur. I'm not going to talk about it. Oh, well, this is not something like we just proposed. John earlier published a paper using biased MD to study MD simulations, basically reached the same conclusion early on. So why should, this simulation looks good, but why anyone should really believe it? So we started comparing notes with existing crystal structures of kinases. The lucky thing is that we have such a rich collection of data of kinase structures. And what we find out is that essentially the conformational space sampled by the DFG conformational space sampled by our simulation largely overlaps with the conformational space sampled by existing crystal structures. So that is a great comfort, give us a lot of confidence. And what this is showing is that by properly order existing kinase structures in terms of the DFG motif, we can make a coarse animation of the DFG flip process. It started with the DFG in conformation, and it started rotating. Now it's it's similar to the vertical intermediate conformation. Basically, that's the conformation where the phenylalanine is trying to enter the binding site, and at the end, the flip has completed. So someone, so the kind of information in a way already existed in the X-ray structures of kinases. And here, of course, if we don't show a time series, we're not really doing these studies. So what I'm showing here is the time series of phi side angles, and there's also a chi angle of phenylalanine, the time series in our simulations. What we show this is where the DFG flip occurred. Okay, so basically before DFG flip, there's a very large-scale wild fluctuations. After the DFG flip, it just died down. So that makes sense, because it's basically saying that the DFG flip is not comfortable after protonation to stay in this DFG conformation. It's trying to get out very, very violently. And when it got out, it became much more comfortable, and it was just, just being happy there. So that's all very nice, but we have to try to understand why protonation plays such a critical role in controlling the DFG motif, and so we started really looking at the environment of the motif, and we trying to come up with some senses of the physics that governs the DFG motif and its conformations. So I think I missed the slide. So. Okay, so that's the one I was missing. And here again, we are looking at the DFG motif in the Ramachandran space. This is the phi side angles of the three residues. The dense black dots are the data points collected from our simulations. And the colored dots are data points reflected from PDB of kinase DFG conformation. And this arrows basically indicate where we started the conformation and where the conformation ended. The trajectory of the simulations in Ramachandran space. So again, we see that the Ramachandran space, our simulations sampled largely overlaps with the Ramachandran space that has been sampled by X-ray structures. But what's particularly interesting is that the red dots represent active kinase conformations in the in 2D view, and we see that the red dots largely populated at this region, which actually is not such a favorable region energetically. This side is much more energetically much more favorable. There's some 2 kcal difference roughly between this location and this location. So that's very curious, because Benoit was talking about loaded spring, and this is a loaded spring. Basically, it says that in terms of the phi side angles of the aspartate residue, in active conformations, it's a loaded spring. It's not that happy. That's interesting. So that caught our attention. So we're gonna use this observation in construction of a simple energetic model to explain the energetics that governs the DFG motif. So now, here's a little energetic model we come up with. It's very simplistic, and so now if we look at the DFG conformation, here the aspartate is in a polar or water accessible environment, which is represented by the red color here, and the phenylalanine is buried in a hydrophobic environment. So that's the DFG conformation. Under this thing, whatever that is, that I was trying to make a mark saying that in this DFG conformation, in terms of aspartate phi psi angles, it's a loaded string. It's energetically unfavorable. Now, if we look at the opposite conformation, in the DFG conformation, we have the phenylalanine in the hydrophilic environment, and we have aspartate in a hydrophobic environment. So in terms of hydrophobicity, DFG out conformation is not favorable. But in terms of the phi psi angles, it is favorable because it removed that loaded spring. So these are these two key elements. And so we constructed an energetic model using these two basic observations, the hydrophobicity and the phi psi string. And the variable element here obviously is protonation, because when the aspartate is protonated, the free energy penalty it has to pay to have the aspartate stay in a hydrophobic environment is much smaller. If it's not protonated, it's a charged residue. You have to pay a huge free energy price. It's almost 10 kcal to have this residue buried in hydrophobic environment. So protonation is the variable element here. And of course, when it's protonated, as suggested by John's crystal structure, it forms the hydrogen bond. So, well, all these things can be semi-quantified by using some kind of standard estimate of hydrophobicity in terms of free counts, which you can construct a little formula to capture what we're trying to say. Now, let's think about something else. Let's think about what is a stable conformation. Oh, this is we have a balance with one very heavy object, one with a very light object. This is, I would say, this is a stable conformation, and in comparison, this is much less stable because a small perturbation on this side could change this conformation. That's what happens. Okay, so now look at what we was trying to say about the DFG motif. Basically, we have the fixed element, which were the phi psi angles that favors DFG out. We have the hydrophobicity, a hydrophobic effect favoring the DFG in. So these two actually, if we do some back of envelope estimate, they are more or less of the same scale. And what you have is that you have a variable element, which is from the protonation state of the aspartate that can govern this conformation. So when it's protonated, you have an out conformation. When it's deprotonated, you have an in conformation. So that's reasonable. Right, so basically I just said that change of aspartate protonation state can switch the DFG conformation. Now let's think about it. Nature designed this very highly conserved motif to make it not such a stable motif conformation-wise, right? So what is nature trying to do? So we're asking the question, is the DFG motif designed to move rather than designed for maximal stability? Actually, there are thermal stability studies. I apologize to those authors because I don't have the proper citation here. They show that when you mutate the DFG motif, you actually enhances the stability, thermal stability of kinases, at least of the kinase system. So I'm asking, is the DFG motif designed to move rather than designed for maximum stability? So is DFG alpha conformation universal? Well, I'm very hesitant to use the word universal, but for lack of better word come to me. Is it generally accessible to protein kinases rather than to the kinases that whose DFG alpha conformation has been captured in X-ray structures? Is the DFG motif an electrostatic controlled switch? Here I didn't put the question mark because I feel more comfortable about that. I think electrostatics does control the DFG motif because the electrostatic environment would affect the pKa of the aspartate in the ATP binding site. And when you affect the pKa, you affect you obviously you can promote or prevent protonation of the aspartate, and therefore promote or not promote the DFG alpha conformation, and vice versa. So if this model is correct, then this DFG motif is electrostatically controlled switch. But the question now is that it's a switch of what, other than the DFG conformation itself. But before we get to that question, let's just make sure that we are not just making up things. That it's a great pleasure that we can obtain experimental data to sort of support this energetic model. So here the third part will be the experimental test of what we have been saying as to the role of DFG protonation in control of this conformation. So the experiment is very simple. The rationale is simple, actually. So we use imatinib, the famous cancer drug, as a probe of DFG conformation because this inhibitor is a famous DFG alpha binder. It only recognizes DFG alpha conformation. So the rationale is this: if we reduce pH, we would promote DFG protonation, therefore promote DFG alpha population, therefore helping imatinib binding. So we are suggesting that the binding, imatinib binding is pH dependent. So here's the experimental data at the left panel. The black line, the black dots are the data for the wild type. Basically, the K-on rate, the binding on rate of imatinib has been measured as a function of various pH. What we're showing is that there's a clear pH dependence here. Okay, when we mutate the aspartate to alanine or to asparagine, it's not its protonation state cannot change anymore. Basically, then it's not affected by pH in the same way, and basically we remove the pH dependence. And the right panel is I show a little formula there, and you can plug in some numbers and basically get some quantitative consistence with the experimental data. Obviously, what's shown is the titration curve, something close to the titration curve, but it's only half of it. Basically, it's a shifted titration curve. So this seems to be working. So if we think about the energetic model, should point out that I used very general things. I didn't use any specific interactions. I just said hydrophobicity, which is general for almost all kinases in that area, because that's where the hydrophobic spine is. And when I said this string of the phi psi angle, that seemed to be pretty common because as suggested by PDB structures. So that seems to suggest that this model is not limited to the Abo kinase. So John's lab recently has shown that this inhibitor binding pH dependence is not limited to Abo and not limited to imatinib. They at least now have one other example showing that a SARC DFG out binder also exhibits the similar pH dependence. So that's encouraging. More detailed analysis of the binding kinetic data suggests that the imatinib binding is a two-step kinetic process, with the DFG flip being the intermediate step. And so, for pharmaceutical people, that seems to be interesting because that says that DFG out binders probably have different kinetic signatures as compared to DFG in binders. But what's interesting to us is that with this understanding, we combine the kinetic data and infer the time scale of the DFG flip, which is of tens of milliseconds. And this time scale is consistent with two NMR studies, to my knowledge. One is John Luigi's study, which showing that there's a conformational change of this time scale in pKa, although John's result doesn't show that it's a DFG flip. It just says something slow is going on. There's another study in P38 kinase also suggests that a DFG motif undergoes conformational change of this time scale. So then this part, well, I'm entering the fourth part, which is very speculative. We don't have all the data to support it, but we're just connecting dots here. I was asking the question that the DFG motif is a switch, but switch for what? So here's the answer I'm trying to give. Basically, we simulated the DFG in conformation and the DFG out conformation. We see is that I'm using these rods. These are conformations collected from our simulations. The red conformations come from DFG in simulation, and the green comes from DFG out conformation. And what this figure is trying to say is that DFG in conformation is very sturdy. And on the other hand, the DFG out conformation, because the loss of the hydrophobic spine is highly flexible, which is shown in this wild switch of the alpha C helix. So conversion from DFG in to DFG out implies a conversion from a rigid state of kinase to a flexible state of the conformation. Now, Joe Adam, a couple of years ago, did a very careful kinetic analysis of the catalytic cycle of pKa, and what he noted is that there's two pauses. When the ATP enters the binding site, it doesn't do catalysis right away. It waits for some 10 milliseconds before it does catalysis. And when the catalysis has been completed, the ADP doesn't get released right away. It pauses for some 10 milliseconds before it releases ADP. And he concluded that these two steps are two conformational change steps. But he didn't comment on what that conformational change is. And here's my speculation is that this might be, these two steps might be the DFG flip and the reverse DFG flip step. Because when you finish the catalysis, the gamma phosphate is gone, the magnesium ion is gone, and you have a pretty dramatic change favoring, because you have positive charge in the magnesium ion. Leaving the binding site, you will promote the aspartic formation and therefore trigger some sort of a DFG conformational change. Well, whether that's a complete flip, we don't have evidence to say anything about that. And when that's this step. I'm sorry. I mean this. When the magnesium leaves the binding site, I assume it leaves the binding site after catalysis. You have DFG flip to the House conformation, which makes the kinase very flexible, and that helps the release of the AADP. And when the ATP enters the binding site along with the magnesium, because they come together, you have magnesium in the binding site, which would reversely induce or stabilize the DFG conformation. So that's a speculation. We need to do more to really pin this down. So now I'm trying to say that again, it's a speculation that the DFG motif might be electrostatic conformational switch controls the mechanical properties of kinases. Well, I don't know how much time I have, but basically I finished the main part of this talk, and I want to give some flavors of the other stuff that our group in Desres is working on. So here I show simulation of SARC kinase with DFG motif pronated. Why pronated? Because we seem to think that the DFG motif is really important, and the pronation seems to be something related to this motif. So we say, okay, what the heck? Just try that, see what happens. What happens is that we for whatever reason, we were able to simulate the alpha-C-out transition. It started from this in conformation with this glutamate lysine solvage intact. It's still intact, but after now this glutamate come out, and it started from the solvage with activation loop arginine, and it stayed there in the rest of a couple hundred nanosecond of simulation. It didn't leave. So. Well, that's very encouraging. That says that we can see real events, structural events in our simulations. But what does it mean? We are still mining these data, and we have some proof, but it's just too preliminary to talk about. We're comparing the out conformation with X-ray structures, which is red, and we're seeing that the alpha-C-out conformation we arrived at is highly consistent with X-ray structures. This is something else. We show that this is completely unconnected with what I was saying, what I was talking about earlier. What we are showing is that when SOC is phosphorylated into the A loop, it's very stable. When it's not phosphorylated at the A loop, it's not stable in terms of RMSD from the initial active conformation. We're talking about all heavy atoms, not just backbone. So why that is the case? Probably because of this its interaction with HRD arginine and with the activation loop arginine. But we don't have a story. We're just presenting some data. I don't know how much time do I have. Negative. So I would just say this. I will try to use 1 minute. So EGFR kinase is famously known that its monomer is inactive, and it can be active only when it forms active dimer. So what we are showing is that our simulation of ABLE and the SARC, which is green and red, are stable. When you start the simulation in the active conformation, it will largely stay there. And when you simulate EGFR, it's never stable. The helix just very readily pops out when in the monomer simulations. So the simulations are smarter than I was hoping. It actually knows the difference between EGFR kinase and the SARC-ABL kinase. So that's good. And when we simulate the dimer, which is this orange line, we see that it stayed in the active conformation. So again, why that is the case, we don't know. This is just very preliminary data, but we're showing that long MD simulations seem to be reaching a place that they can really help to study biology. Thank you very much.
This is a beautiful example of metastability of work. I just want to point out, this is actually, in many ways, a universal property of kinases and probably regulatory proteins in general, because the selection is for switchability. And you can't have switchability if you have deep wells. You need states that have been destabilized by raising the bottoms of the wells. This one was done by hydrophobicity and by the protonation. So there are other methods that are used otherwise. For example, the regulatory subunits PKA. But I think it's been driving me nuts structurally, because it means we get some large changes with relatively small perturbations, and they're harder than places to predict without going into the level of detail that you're going through right now.
Yep. Yeah, that's a beautiful talk. If you were, I guess you and Marcus made that aspartate to asparagine mutant in ABLE. The prediction would be, based on my naive interpretation of your work, is that should really dramatically promote binding of imatinib to almost any kinase, even if it increases the activity. Does it?
It doesn't. It seems to be not the case, and it came as a surprise to us either. And we tried to justify it this way. Asparagine has a higher hydrophilicity compared to protonated glutamate. So it basically said that by the penalty of moving the asparagine from the ATP binding site to a hydrophobic place would have to pay higher angle penalty. That's why in the well, that's why in our theoretical model, this asparagine actually does have a lower expected K-on compared to say the other construct, because it has a higher hydrophilicity. If you plug in the numbers, then it turns out.
Yibing, I have two questions. So there are a lot of kinases, actually not a lot of kinases, but at least some kinases that have a tryptophan instead of the glycine. So what would you predict in that case? I mean, would the CMG flip happen? Would it happen or not happen? Or what would your prediction be? Second question is, how is the DFG flip correlated with the opening and closing of the lobe? I mean, have you, of the two lobes, have you seen any correlation? Or?
What's the second question?
So if you had a measure of how open or closed the N and C terminal lobes of the kinase are, and see if that opening and closing of the two lobes are somehow correlated with the DFG in and out? I mean, do you see that correlation?
Yes, yes.
Okay.
A DFG outcome has generally much open conformation and more flexibility.